The United States generates more than 300 million tons of waste each year, and most of it is never recycled. In reality, only a small fraction of plastic is properly processed. The rest ends up in landfills, is incinerated, or simply disappears from your view. Garbage trucks quietly take everything away, leaving things clean and orderly, as if the problem has been solved. But what really happens after it leaves your sight? Behind the scenes, a massive system is at work. Facilities sorting tens of thousands of tons of waste every day, landfills as vast as cities, and streams of waste that silently leave the United States for destinations far beyond its borders. For years, we've believed that recycling was the solution. Just put things in the right place, and the system would handle the rest. But when you look closer, the story is far more complicated. This is not just the journey of recycled waste. It's about how a system operates, reaches its limits, and leaves behind consequences that few ever see. Today, let's explore what really happens after your trash leaves your hands, together with Terran Works. Each day, the United States generates an enormous amount of waste, averaging more than 2 kilograms per person. This is one of the highest levels of consumption and disposal in the world, directly reflecting a lifestyle heavily dependent on packaged goods, single-use plastics, and fast consumption. However, the way this waste is managed is not consistent across the country. Only about 1/3 is recycled or composted, while the majority is still sent to landfills, and a smaller portion is processed through incineration to recover energy. The U.S. waste management system is highly decentralized, relying on individual states and local governments rather than a unified national strategy. This leads to clear disparities between regions. States like Pennsylvania and Ohio have high landfill rates and even receive waste from other states, effectively becoming major collection hubs within the system. Meanwhile, populous states such as California generate the largest volumes of waste in the country, placing continuous pressure on waste management infrastructure. This imbalance makes waste not just an environmental issue, but also a challenge of management and cost. When some regions are forced to handle waste beyond their capacity, the entire system becomes interdependent, forming a complex network of waste processing. And within that complexity, the system's weaknesses begin to emerge, raising serious questions about the true effectiveness of how the United States currently manages its waste. But as the system becomes more complex and dependent on many factors, a crucial part of it lies in how people use it. Not every problem starts at a factory or a landfill. It often begins right at the trash bin in each household. For many years, people in the United States have been encouraged to recycle more. Just put items in the right bin, and the rest will be taken care of. But this oversimplified mindset has led to a common phenomenon known as wishcycling. Wishcycling combines wish and recycling, and refers to the act of tossing an item into the recycling bin simply because you hope it can be recycled, not because you're sure it actually can. Instead of checking local guidelines, many people take a guess, assuming the system will sort it out. As a result, many unsuitable items end up in the recycling stream. Greasy food containers, thin plastic bags, multi-layer materials, or products that aren't recyclable at all. When these enter the system, they are not only rejected, but can also contaminate entire batches of otherwise recyclable materials, rendering them unusable. From these small, everyday choices, wishcycling has become one of the biggest factors reducing the overall efficiency of the waste management system. What's striking is that most of these actions come from good intentions, yet they ultimately have the opposite effect. And when unsuitable materials keep entering the system, the question is no longer whether they can be recycled, but what actually happens to them next. The answer begins at the very first step of the entire process: collection. Whether an item is placed in the bin with the right intention or not, the system handles it all in the same way. In the United States, residential areas are served by fixed collection routes, where waste from hundreds, even thousands of households is gathered into a single load. In many places, all recyclables, paper, plastic, metal, and glass, are placed together in a single bin under a single stream system. This makes recycling easier for residents, but it also allows mistakes from wishcycling to spread quickly. Even a small percentage of unsuitable materials can affect the entire stream right from the collection stage. By the time garbage trucks finish their routes, they carry not only potentially recyclable items, but also the accumulated errors from individual households. From that point on, the entire mass is transported to processing facilities, where the real sorting begins, and where small mistakes start to compound into a much larger problem. When garbage trucks unload their contents at the receiving area, the journey is far from over. It is only entering a more critical phase: sorting. At central processing facilities, this mixed stream of waste is fed onto massive conveyor belts, where everything begins to be separated layer by layer. Materials that once seemed indistinguishable, paper, plastic, metal, glass, must now pass through a series of processes designed to identify and separate them as accurately as possible. Mechanical and automated systems play the primary role at this stage. Powerful magnets pull metals out of the waste stream, air jets separate lighter materials like paper and plastic, while optical sensors can identify different types of plastic based on their surface properties. Alongside these technologies, human intervention remains essential. Workers stationed along the queue remove items that machines cannot properly handle. But this is also where the consequences of wishcycling become clearly visible. Contaminated, missorted, or non-recyclable materials are not only rejected, but can also disrupt the entire sorting process. And it is here that the line between recyclable and true waste begins to take shape. But separating materials is only the first step. To actually be recycled, they must go through another critical stage: cleaning. After sorting, materials such as plastic, metal, and glass often still carry contaminants, from dirt and dust to grease and leftover food. If these are not removed, they can ruin the entire recycling process in later stages. At this point, specialized cleaning systems come into operation. Plastics and metals are typically washed using high-pressure water or chemical solutions to remove adhered residues. Paper and cardboard follow a different process, where they are pulped and filtered to eliminate impurities. Meanwhile, glass is cleaned and separated from non-conforming fragments before further processing. However, not all materials can be saved at this stage. Items that are too dirty, heavily contaminated with oil, or mixed with multiple material types are often rejected entirely. This means that even after passing the sorting stage, they still cannot continue on the recycling path. It is during this cleaning stage that the consequences of wishcycling once again become clear, as early mistakes continue to reduce the real recyclability of the entire system. However, not all materials make it through the cleaning stage. A portion of them, due to excessive contamination or failure to meet technical standards, is removed from the recycling stream. From that point on, their journey no longer follows the recycling path, but shifts toward a different destination: final disposal. In the United States, one common option is to send them to waste-to-energy plants. Here, waste is processed at high temperatures to reduce its volume and recover energy in the form of electricity or steam, a system known as waste-to-energy. This method helps significantly reduce the amount of waste sent to landfills, but it is also widely debated. At this stage, early mistakes are no longer minor issues. They become decisive factors in whether materials can actually be recycled or not. After passing the cleaning stage, only materials that meet quality standards can continue their journey into the final phase of the cycle: reprocessing. Here, what was once considered waste begins to be transformed into new raw materials. Plastic is shredded, melted, and formed into recycled pellets, ready to be manufactured into bottles, packaging, or textile fibers. Metals such as aluminum and steel are melted at high temperatures and recast into new products with nearly unchanged quality. Paper and cardboard are processed into pulp, where ink and impurities are removed before being reformed into new paper products. However, this process is not as closed-loop as many people imagine. With each recycling cycle, especially for plastics and paper, the quality of the material tends to degrade. This means they cannot be recycled indefinitely, but only for a limited number of cycles before eventually becoming waste. Because of this, the reprocessing stage is not just the end of one life cycle, but also the point that determines whether a material can continue existing within the system or be permanently removed from it. It highlights the fact that material life cycles are finite, rather than endlessly renewable, as many assume. But even when a portion of waste can be turned back into new materials, the story does not end there. Recycling is, in reality, not always a closed-loop process that happens entirely within national borders. Not all sorted and cleaned materials are processed domestically. More importantly, recycling is not always economically viable. When processing costs rise, or when certain materials are not valuable enough to be recycled within the country, the system turns to another solution: exporting them beyond its borders. In the United States, a significant share of waste, especially plastics, is not fully processed domestically, but is instead shipped to other countries. In theory, these materials are still considered recycled. In practice, however, their journey is often far more complicated and does not always end as expected. From this point on, waste management is no longer just a national issue. It becomes part of a global system where external market changes can directly influence how waste is handled domestically. Common destinations have included China, Malaysia, Vietnam, Indonesia, and Thailand, places where labor costs are lower and environmental regulations, in some cases, less strict. For many years, this model appeared to function smoothly. Waste was collected, sorted, and what could not be processed domestically was shipped abroad as a way to relieve pressure on the local system. But that stability did not last indefinitely. As more countries began to recognize the environmental impact of accepting foreign waste, they gradually tightened regulations. The turning point came when China, a country that once handled a large share of the world's recyclable waste, introduced a ban in 2018 on importing many types of waste. From that moment on, a critical link in the global system suddenly disappeared. Waste could no longer be easily exported as before. While domestic waste volumes continued to grow every day, processing facilities began to become overwhelmed, recycling costs increased sharply, and many cities were forced to reduce or completely shut down their recycling programs. What was once seen as an efficient operating system began to reveal its limitations. There were no longer enough destinations to send waste, insufficient capacity to process it domestically, and no clear alternative solution. From here, waste management was no longer just a technical process. It had become a problem that was increasingly difficult to control. As these changes began to spread, their impact was no longer just systemic. It started appearing directly in everyday life. In the United States, many cities faced sharply rising waste management costs. When recycling was no longer economically viable, separate collection programs were reduced or discontinued, causing more and more waste to be sent directly to landfills or incinerators. Pressure also mounted on processing facilities. Landfills that were already nearing capacity had to absorb even greater volumes of waste, raising concerns about environmental pollution and sparking opposition from local communities. In many areas, proposals to expand landfills or build new treatment facilities faced strong public resistance. Beyond environmental concerns, the issue also extended into economics. Local governments were forced to allocate larger budgets just to maintain the system, while overall efficiency continued to decline. The lack of coordination between states made management even more complex, as each region adopted different approaches. From this point on, waste was no longer something that disappeared after collection. It became a visible, tangible issue that directly influenced how cities operate and develop. But when looking at the bigger picture, the story is not only about problems and limitations. Despite its shortcomings, recycling still plays an important role in reducing environmental pressure in the United States. When done properly, It helps cut down the amount of waste sent to landfills, reduces the need to expand already overburdened disposal sites, and lowers the risk of soil and water pollution. Beyond that, recycling also helps conserve significant natural resources. Metals like aluminum can be recycled using far less energy compared to mining and producing new materials, while recycled paper reduces pressure on forests and water supplies. Even plastics, though more difficult to recycle, can still be reused in certain cycles, contributing to a reduction in overall environmental waste. More importantly, recycling creates a circular flow, where materials are not immediately discarded, but have a chance to re-enter the production system. This not only extends the life cycle of resources, but also reshapes how people perceive waste, not just as something to be thrown away, but as something that can still be utilized. Although it is not a perfect solution, recycling remains one of the key tools preventing the system from completely breaking down, and a crucial part of how modern society is trying to adapt to ever-increasing amounts of waste. While the United States continues to operate a decentralized and inconsistent waste management system, many countries in Europe approach the issue in a more structured and unified way from the very beginning. In these countries, waste separation is not optional, it is mandatory. Residents are required to sort materials at the source, separating paper, plastics, and organic waste. And in many cases, non-compliance can result in specific fines. This leads to a significantly cleaner waste stream compared to the mixed collection model commonly used in the US. Beyond consumers, responsibility is also pushed back onto producers. Many European countries implement an extended producer responsibility (EPR) model, requiring companies to cover the costs of collecting and treating their products after they become waste. This creates a strong incentive to design products that are easier to recycle from the outset. As a result, recycling rates in many European countries are noticeably higher, while the amount of waste sent to landfills is reduced to a minimum. However, the key difference is not only in technology or regulation, but in how the entire system is designed to reduce waste at the source, rather than simply managing it after it has already become a problem. Between Hawaii and California lies an area known as the Great Pacific Garbage Patch, a body of water covering roughly 1.6 million square kilometers, nearly twice the size of the state of Texas, or 3 times the size of France. This is not a solid, continuous, floating island of trash as many people imagine, but rather an accumulation zone where ocean currents gather plastic from all over the world. The problem is not only the amount of plastic visible to the naked eye, but the continuous fragmentation process under the effects of ultraviolet radiation, waves, and abrasion, which produces microplastics of ever smaller sizes. These microplastic particles can enter the marine food chain, be absorbed by plankton, bioaccumulate across trophic levels, and ultimately return to the human body. In ecological logic, every year of delay in cleanup means that all future intervention efforts become more complex and more costly. And humanity has delayed this process for more than 7 decades since plastic began to be produced and exploded on a global scale in the mid-20th century. Scientists estimate that this area accounts for just 1% of the ocean's water, yet concentrates around 1.8 trillion plastic pieces, with a total mass of between 79,000 and 100,000 tons. For decades, experts have been nearly unanimous in agreeing that cleaning this area is impossible. Estimated costs run into tens of billions of US dollars, and if traditional methods such as ships and nets were used, the process could take thousands of years. In terms of scale and physics, this is a problem that exceeds the capacity of any solution ever proposed. Against this seemingly hopeless backdrop, a 16-year-old Dutch boy named Boyan Slat appeared and proved everyone wrong. In 2011, during a scuba diving trip in Greece, Slat expected to witness the Mediterranean ecosystem, but instead, what he saw more frequently than fish were floating plastic bags. They were everywhere, repeating themselves to the point of creating a disturbing distortion of the ocean's natural order. For most teenagers, that moment would likely have ended as a passing annoyance. But for Slat, it led to a very simple, even naive question. Why can't we just clean this up? That question did not fade after a few days. It stayed with him for years, gradually becoming the core of the entire journey that followed. Rather than merely protesting pollution, he began to seriously study why experts believed that cleaning the ocean was impossible. Slat analyzed costs, assessed logistics, and examined the technical limitations of traditional methods. It was precisely during this process that an idea, so simple it initially seemed absurd, began to take shape. Instead of chasing plastic across millions of square kilometers with ships and nets, why not let the ocean currents do the work? If barriers were designed intelligently enough, natural flows could concentrate the plastic for collection, eliminating the need for a massive fleet of ships consuming fuel and manpower. This was an approach that ran counter to conventional intuition, yet aligned perfectly with how the ocean itself operates. Slat went on to study aerospace engineering at Delft University of Technology in the Netherlands, where he continued to develop his idea. In the fall of 2012, he won the Top Engineering Design Award for his ocean cleanup concept. On October 5, 2012, at the age of 18, he stepped onto the TEDx Delft stage and delivered an 11-minute talk titled, "How the Oceans Can Clean Themselves."
However, I believe the Great Pacific Garbage Patch can completely clean itself.
For several months, the video received almost no attention, garnering only around 2,000 views. But in February 2013, news outlets discovered it, and the video exploded almost overnight. Donations began pouring in within days, forcing Slat to make a major decision: continue his engineering degree or drop out to pursue the goal of cleaning the ocean. At the time, he had only $300 in savings. Slat chose the ocean. Just days after the video went viral, he received $90,000 in donations, and by October 2013, when the TEDx talk surpassed 1 million views, the ocean cleanup was officially founded. Before calling for funding on a global scale, the newly founded organization wanted to prove that its idea could actually work. On June 3, 2014, a 528-page feasibility study conducted by around 70 scientists and engineers was published, and a crowdfunding campaign was launched simultaneously. The response exceeded all expectations. Within 100 days, 38,000 donors from 160 countries had contributed. And by September 15, 2014, the total reached $2,154,282, making it the most successful nonprofit crowdfunding campaign in history at the time. At the same time, Slat made a bold promise to clean up half of the Great Pacific Garbage Patch within 10 years, a goal that even supporters considered extremely ambitious. In August 2015, the Mega Expedition campaign was launched, with 30 vessels operating across the Pacific Garbage Patch, collecting more data than all scientific research from the previous 40 years combined. These findings quickly overturned many earlier assumptions. The garbage patch was not a solid mass, but more like a plastic soup dispersed across a vast area. Its composition was also surprising. Fishing nets accounted for 46% of the mass, and between 75% and 86% of the plastic originated from offshore fishing activities. The first prototype tests soon revealed serious problems, ranging from leaking air chambers to failed anchoring systems, demonstrating that the original concept required a far higher level of engineering than anticipated. In response to these challenges, the idea of a 100-kilometer seabed anchored barrier was abandoned and replaced with free-floating systems approximately 2 kilometers long, using deep-sea anchors. System 001, nicknamed Wilson, was deployed in 2018 amid high expectations. However, the system quickly exposed major limitations. It failed to maintain an appropriate speed relative to the plastic, allowing debris to flow in and then drift back out. By the end of 2018, an 18-meter section broke due to material fatigue at welded joints, forcing the system to be towed back to Hawaii after collecting only about 2,000 kilograms of plastic over 4 months. Media coverage turned critical, and a 2018 survey found that not a single ocean plastic expert fully supported the project, with more than 25% considering it a bad idea. SLAT described this failure as an unplanned learning opportunity. The team returned to the drawing board and identified the core issue. The system needed to move more slowly than the plastic in order to retain it. From this insight, System 001B was developed, much smaller and equipped with a parachute anchor to create drag. When launched in 2019, this system, for the first time in history, successfully captured and retained plastic from the Great Pacific Garbage Patch, including microplastics as small as 1 millimeter. This marked the moment of transition from theory to real-world proof.